Okay, in Module 18J, I'm just going to work additional practice problems covering the concepts in the Aqueous Equilibria modules. So if you need some extra practice or want to see some extra examples, here you go. Which compound below has the lowest molar solubility? Which one has the greatest molar solubility? Well, let's look at it. What do I mean by molar solubility? I mean how much is actually going to dissolve. So let's look at, that should definitely be an AGI. Just realized that that is written as an O. I don't know how I didn't notice that before. Let's change that to an I. That should be AGI. And the KSP is 8.3 times 10 to the negative 7. So let's first look at, we're going to look at each one individually and figure out its molar solubility. So for AGI, silver iodide, we know this will form silver ions and iodide ions. We don't have any silver ions or iodide ions to start. We produce S amount of each one, so at equilibrium we have S for each one. KSP is equal to silver plus times I minus, so S squared, and this is equal to 8.3 times 10 to the minus 17. Solve for S, and S has a value of 9.1 times 10 to the minus 9th. And I'm going to write that underneath here. Because I'm going to need this space to work. Let's go ahead and calculate it for the others as well. So if you need to write that down, please pause the video. Let's look at calcium or cadmium hydroxide. CdOH2, Cd2 plus, 2 moles of OH minus. Your rice chart. We don't have any cadmium to start, but we will produce S amount. Now, hydroxide, here's the trick. Hydroxide is naturally in water. So I have 10 to the minus 7th moles of hydroxide ions in water, plus 2S, and 2S plus 10 to the minus 7. I have two options here, approximation number 1, approximation number 2. Let's work them both out. Approximation number 1 is assuming 10 to the minus 7th is really, really small compared to 2S. My KSP is equal to my cadmium 2 plus concentration times my hydroxide concentration squared. If I assume that 10 to the minus 7th is really small, this would be S times 2S squared, which is the same as 4S cubed, and this would be equal to KSP 5.9 times 10 to the minus 15. Solve for S, and I find my S to be 1.1 times 10 to the minus 5. I'm also going to do it with approximation number 2, just to check. That is where we are going to assume that 2S is very, very small compared to 10 to the minus 7. S times 10 to the minus 7 squared equals 5.9 times 10 to the minus 15. And if I solve this out, S would be 5.9 times 10 to the minus 1. How do I choose which one's correct here? Well, you compare these two numbers. Does this S value look a lot bigger than 10 to the minus 7? Yeah, it's a lot bigger. Does this S value look a lot smaller than 10 to the minus 7? No. This approximation is valid. Therefore, the molar solubility of cadmium hydroxide in water, S equals 1.1 times 10 to the minus 5th. When you have hydroxide like that, you have to check both ways. You just don't know if the hydroxide in water is bigger or not. So you will have to check both ways. It does depend on your system. Okay, I need to erase all this. And the last example, or the last system, SR3PO42. So strontium phosphate in equilibrium with 3 moles of SR2 plus and 2 moles of PO43 minus. Set up your ice chart. There's no common ions here, so don't have to worry about that. Plus 3s, plus 2s, 3s and 2s. Your KSP, 1.0 times 10 to the minus 31, really not very soluble. SR2 plus, quantity cubed. PO43 minus, quantity squared. 3s cubed times 2s squared. We've already got the 1.0 in there. Cool. So 3s cubed is the same as 27s cubed. 2s squared is the same as 4s squared. 27 times 4 gives me 108. And that is s to the 5th now, equals 1.0 times 10 to the minus 31. Solve for s, I get an s value of 2.5 times 10 to the minus 7. Now I'm going to compare the 3 values I've got. Hopefully you paused that before I erased that on you if you needed to write it down. But now let's compare these. I've got 9.1 times 10 to the minus 9th is the smallest. I've got 2.5 times 10 to the minus 7 in the middle. And I've got 1.1 times 10 to the minus 5 as the largest. What do these values mean? This is your molar solubility. How much will dissolve? The greater the number, the greater the solubility, the more it will dissolve. So which one has the lowest molar solubility? Silver iodide. Which one has the greatest molar solubility? Cadmium hydroxide. Don't forget, for that cadmium hydroxide, we had to check it both ways. We had to do approximations each direction to see which was valid. Okay. The KSP of PbCl2 lead 2 chloride is 1.7 times 10 to the minus 5th. In which of the following aqueous solutions would you expect the PbCl2 to have the lowest solubility? In this situation, you're talking about lowest solubility. What can affect solubility? We know pH can affect solubility, but we've got chloride here, so we're not really worried about that. We are, however, even with pH, also talking about common ion effect. Does any of these have lead 2 plus in them? Or Cl minus in them? That is your common ions. That can affect your solubility. So pure water? No, it doesn't have either one in it. Let's look at PbCl2. Pb2 plus. Cl minus. There's 2 moles of Cl minus there. And I'm going to look at each system here. So A, B, C, D, and E. A doesn't have anything. No lead, no chloride. B doesn't have any lead in it. but it has 0.3 molar NaCl, which is the same as 0.3 molar chloride. C doesn't have any lead in it, but it's got 0.2 molar magnesium chloride, which is 0.4 molar chloride ions, because remember, 2 chloride ions to every 1 magnesium chloride. D doesn't have any lead in it, but it does have aluminum chloride in it. It's got 0.15 molar aluminum chloride, which is the same as 0.45 molar chloride ions, because the 1:3 ratio of chloride ions to aluminum chloride. And lead-2 nitrate, it's a 0.1 molar solution of lead-2 nitrate. It has 0.1 molar lead in it and no chloride in it. So which one's going to have the largest effect here? The one that has the highest concentration of a common ion. Which one's going to have the lowest solubility? 0.15 molar silver chloride, or aluminum chloride. Which of the following acids would be the best choice to combine with its sodium salt to make a buffer with a pH range 4.5? 4.25, I can read. So, buffer range is plus or minus 1 from the pKa value. When I look at these, I need a pKa value that is within the range of plus or minus 1, 4.25, which means anywhere from 3.25 to 5.25 is valid. 1.95, not valid. 3.34 is valid. 3.74 is valid. 7.54 is not valid. So we're down to nitrous acid and formic acid. So nitrous acid and formic acid can reach a pH of 4.5 buffer. .25. I keep forgetting that too. I don't know why, but I do. Within 1 pH unit. But it's on the limits to be able to pull this off for nitrous acid. Like this is valid from 2.34 to 4.34. This is valid from 2.74 to 4.74. Formic acid is your better choice. Because it's fitting within that range even better. What ratio of sodium acetate, no, that's not even acetate, that's formic acid. Sodium formate and formic acid will be required to make a buffer with a pH of 4.25. And it gives me the pKa value of formic acid. So I want the ratio of these two. I'm going to use Henderson-Hausbach because I like that equation. Remember, this equation is valid when you have a buffer, meaning you have an acid and its own conjugate base, or a base and its own conjugate acid. pH is equal to pKa plus the log of the concentration of base over the concentration of acid. I want a pH that's 4.25. I know my pKa value is 3.74. So I'm going to solve this. This difference, 4.25 minus 3.74, is going to give me a difference of 0.51. That equals the log of the base over acid. I need to undo that log. So 10 raised to the 0.51 equals 10 raised to the log of the base over acid concentration. And that gives me 3.23 is equal to the ratio of base to acid. What does that mean? How is that helpful to me? What that means is that my concentration of base is equal to 3.23 times that of my acid. So if I need to actually make this buffer, let's say I chose to make a 1 molar formic acid. Then my base would have to be 3.23 molar sodium formate. It's telling you the ratio of the two to each other. The base will be 3.23 times more concentrated than your acid. Once you have molarity, you can choose the volume of buffer you want to make. And from there, with the volume of buffer you want to make, you can figure out the grams or milliliters are required to actually prepare this buffer. What is the minimum hydroxide concentration necessary to just begin to precipitate magnesium 2 plus with a 0.059 molar concentration from seawater? I want the molarity of hydroxide. So I need the moles per liter of hydroxide, right? Moles of hydroxide per liter of hydroxide solution. 0.059 moles of magnesium 2 plus per 1 liter of solution, because that's what molarity means. And this is the magnesium 2 plus solution. I'm going to assume I have 1 liter. Why? Because it doesn't tell me amount. It only wants concentration, so I'm just going to assume 1 liter to make my life easy. I also know that 1 mole of magnesium ions reacts with 2 moles of hydroxide ions to form magnesium hydroxide. So I know I need 2 moles of hydroxide ions to every 1 mole of magnesium ions. So this cancels out this cancels out this. Now I've got moles of hydroxide, and I need concentration. So 1 liter, why not? 0.12 moles of hydroxide per 1 liter of solution. Technically, when I did this math, this math technically came out to 0.118 molar, but I need 2 sig figs. So that's how I get 2.12 molar hydroxide ions needed to just begin to precipitate that magnesium chloride from solution, or magnesium ions from solution as magnesium hydroxide. Calculate the mass of sodium acetate that must be added to 500 mils of 0.2 molar acetic acid to make a buffer with a pH of 5. The pKa value of acetic acid is 4.74. I'm going to use Henderson-Hasselbalch. So pH equals pKa plus the log concentration of base over concentration of acid. You don't have to use Henderson-Hasselbalch. I just like it because it's faster. Plug in what we know. We want a pH of 5, and we know the pKa value is 4.74. We want to know the base. We need to figure out the mass of sodium acetate, so we need to figure out the concentration of base. And we know that we have 0.200 molar acetic acid. 5 minus 4.74 is 0.26. I'm going to raise both sides to 10 to undo that log. This gives me 1.8 equal to the concentration of base over 0.200 molar. Concentration of base here, 1.8 times 0.2, 0.36 molar. So I need a 0.36 molar sodium acetate solution. I have 500 mils total. But I need to know the number of grams. Why? Because when I say mass, I mean grams. Moles of NaCH3COO divided by 1 liter of solution. I have 500 mils of solution, 0.5 liters. Add up the molar mass of sodium acetate, not just acetate. Don't forget the sodium in there. We need the sodium. I can't just measure out acetate ions in the lab. I have to measure out sodium acetate. 82.01 grams. To 1 mole of sodium acetate. 14.8 grams of sodium acetate. So if I have a 500 ml solution of 0.2 molar acetic acid, if I want a buffer with a pH of 5, I need to add 14.8 grams of sodium acetate to the solution to prepare that buffer. What is the pH after 0.150 moles of NaOH is added to 250 mils of a buffer containing 0.5 molar acetic acid and 0.5 molar sodium acetate? I am adding a base to a system that has an acid and its own conjugate base, which means that I need to do a BCA table. I will tell you on here, assume volume is negligible of the NaOH to make it easier. If I'd given you volume, it would be different, but I didn't, so you can assume it's negligible when I don't provide that. But you need to recognize that we need to do a BCA table. That base is going to react with the weak acid in solution, the weak acid being acetic acid, which I represent as HA, OH minus being the NaOH I'm adding. That will react to create or produce more conjugate base and water. Originally, we had a 0.5 molar acetic acid solution and 250 mils of that, which is the same as 0.125 moles. And for hydroxide, I added 0.150 moles to the system. I also have 0.125 moles of conjugate base because I have a 0.5 molar solution and it's 250 mils of it. When you look at these two numbers, we see that the 0.125 is the smallest number, so minus 0.125 moles, minus 0.125 moles, plus 0.125 moles. And after the neutralization, I don't have any of my weak acid left. I still have 0.025 moles of hydroxide remaining, and I now have 0.250 moles of my acetate, or my conjugate base. Here's the trick. You've got a strong base with a weak base. This goes back to that concept of Le Chatelier's principle. Why is a weak base causing a solution to be basic? This conjugate base, A minus, your acetate, the conjugate base of acetic acid, normally reacts with water, undergoing equilibrium expression, where it forms acetic acid plus hydroxide. It's this formation of hydroxide that's causing the solution to be basic. But I have a common ion effect. So we've got this hydroxide in solution from the left after the neutralization reaction. There's still hydroxide left, which means that I've added some of this into solution. What's going to happen to this equilibrium? Le Chatelier's principle tells us it's going to shift backwards. What that really means is very little, if any, of that A minus is actually going to be able to successfully react with water to produce HA and OH minus. It's going to be in such a negligible amount that the pH of the solution is going to be completely controlled by the presence of the hydroxide from the strong base. So I take the moles left over from that strong base, divide it by the volume of solution, one second. I just realized that the numbers I've written on your PowerPoint and the numbers in my notes are different. So they might be different all over. Okay, that was correct. So your moles are correct. That part's good. I need to just recheck my math for the new molarity. 0.025 divided by 0.25 liters gives me a 0.100 molar OH minus solution. Negative log of 0.100 molar gives me 13.00. I have 2 sig figs here, so this actually needs 2 sig figs. Should be 0.10, 13.00 to keep your sig figs right. And, sorry, now I'm writing down pH because I'm moving ahead of myself. 1.00, which is pOH. Therefore, your pH is equal to 13.00. Basically, it's kind of like you've passed your equivalence point on the titration curve, and now the pH is completely controlled by the added base to solution. What is the pH after 4 grams of NaOH is added to 250 ml solution of a buffer containing 0.5 molar acetic acid and 0.5 molar sodium acetate? Again, because I wrote this in my notes, but not on the slides, I apologize. Assume the volume of sodium hydroxide is negligible. If I've got 4 grams of NaOH, I really need moles because I need to do a BCA chart. So 1 mole of NaOH weighs about 40 grams. .100 moles of NaOH. Why do I need to do a BCA chart? Because I am adding base to a system that has an acid that is not its conjugate. Therefore, it will undergo a neutralization reaction, which is a BCA table. Since I'm adding base, it's going to react with the acid in the system, in this case acetic acid, but I'm just going to write HA because it doesn't matter what acid it is, plus OH minus to represent the sodium hydroxide, giving me A minus plus H2O liquid. I have a 250 ml beaker, or 250 mils of the buffer solution, and it's 0.5 molar acetic acid, which means I have 0.125 moles of acetic acid. It's also 0.5 molar sodium acetate in 250 mils, so 0.125 moles of sodium acetate. Or in this case, in our BCA chart, acetate, because we're looking at net ionics for this. Hydroxide, I just determined I have 0.1 mole of this. So minus 0.100 moles, minus 0.100 moles, because that's the smallest number, plus 0.100 moles. This gives me 0.025 moles of acid remaining. And I now have 0.225 moles of my base. Because I have both acid and base present, I have a buffer. And I'm going to use Henderson-Hasselbalch. pH equals pKa plus the log, concentration of base over the concentration of acid. I'm trying to find pH. The pKa value of acetic acid is 4.74. That would be provided on any assessments. But if you're unsure, you can either look up pKa or look up the Ka value and then take the negative log of it to find pKa. Your base concentration, 0.225 divided by 0.250 liters. Your acid concentration, 0.025 divided by 0.250 liters of solution. We get an overall pH here of 5.69. So we're almost outside of that buffer range. We've added enough base to it that we've almost destroyed the buffer. We're still technically within it, but not very close anymore. What is the pH after 20 mils of a 3 molar HCl solution is added to 250 mils of a buffer containing 0.5 molar acetic acid and 0.5 molar sodium acetate? I've got 20 mils, 3 molar HCl. You need to know the number of moles of HCl. That gives me 0.60 moles of HCl. I am adding HCl to a solution that has an acid and its conjugate base, but not the conjugate base of HCl. Therefore, I need a BCA chart. A neutralization is going to occur. I'm going to use H3O plus to represent the strong acid. And this time, it's going to react with the conjugate base in solution. Remember, if you're adding acid, it reacts with base. Acids and acids do not react. Bases and bases do not react. Acids react with bases. So in the previous example, I had it react with acetic acid because I was adding base. Now I'm adding acid. It must react with the acetate, forming acetic acid and water. I have 0.060 moles of H3O plus. You can also, how many moles of HA? 0.50 moles of HA to 1 liter times 0.250 liters of solution gives you 0.125 moles of HA. And the same process would follow for the number of moles of A minus because the concentration of acetic acid and sodium acetate is the same in solution. So 0.125 moles, 0.125 moles. Minus 0.060 moles because it's the smallest number. Plus 0.060 moles on the product side because that's how much acetic acid I'm producing. That leaves me with no base left, or none of my strong acid left. I now have 0.065 moles of conjugate base remaining, and I now have 0.185 moles of my weak acid. I've got both weak acid and its conjugate base, so I've got a buffer. So I'm going to use Henderson-Hasselbalch. pH equals pKa plus the log of the base over the acid. Again, you don't have to. You can set up a rice chart if you'd like to. I just don't prefer it. pH is equal to 4.74 plus the log. The concentration of my base is 0.065 moles divided by 0.250 liters divided by the concentration of acid, 0.185 moles divided by 0.250 liters. And the pH comes out to 4.29. Notice when I added base to the buffer, the pH increased. Now I'm adding acid to this buffer, the pH is decreasing. Makes sense, right? When I add acid to it, it reacts with the conjugate base, decreasing the concentration of conjugate base, increasing the concentration of the weak acid, therefore more acid in solution, lower pH. When I added base, it reacted with the weak acid in solution, producing more conjugate base. So the conjugate base concentration was higher than the weak acid concentration, therefore the pH increased. 25 mils of a 0.1 molar NaOH solution is added to a buffer made of 500 mils of 0.30 molar NH4Cl and 500 mils of 0.3 molar NH3. What is the resulting pH of the solution? Kb for this, by the way, Kb of ammonia is 1.8 times 10 to the minus 5. So, what do I got going on here? Let's see. I need to know number of moles of base. I've got a 0.1 molar, so 0.1 moles per 1 liter OH minus solution, and I'm using 0.25 mils of that, or 0.025 liters of that, 25 mils of that. That gives me 0.00250 moles of OH minus. I've also got 0.3 molar NH4 plus per 1 liter of solution. And I'm using 500 mils of that, or 0.5 liters of that, which gives me 0.150 moles. And this also equals the number of moles of ammonia because they're equal in solution. I have 0.3 molar ammonium chloride and 0.3 molar ammonia in that 500 ml solution. When it says buffer made of this and this, that's not written very well. I meant that that's 500 mils total, not 1,000 mils total. I meant it should probably be best to just write it as this. Like, ignore that part. I mean, that's 500 mils of that total solution. Now, I'm adding base to the buffer. When you're adding base to a buffer, it's going to go through a neutralization reaction. It's going to react. I'm adding base to a system that has a weak base and a conjugate acid, but not the conjugate acid of the base I'm adding. Therefore, I need a BCA chart. My base, my hydroxide, is going to react with the acid in solution, not the base. The acid in solution is the NH4 plus. NH4 plus is the conjugate acid of ammonia. Single-headed arrow because it's a neutralization reaction, forming more ammonia and water. Initially, I had 0.00250 moles of hydroxide, 0.150 moles of ammonium, and 0.150 moles of ammonia. Subtract the smallest number, 0.00250 moles, 0.00250 moles, and plus 0.00250 moles. So 0.00250 moles of hydroxide will react with that many moles of ammonium, producing that many moles of ammonia. After this reaction is complete, I will have 0.1475 moles of ammonia and 0.1525 moles of ammonium, and then ammonia. These words are so similar to me. So I gave you the KB. This does have a buffer, which is nice. I can use Henderson-Osbach, but be careful here. The equation still remains pH equals pKa plus the log of the concentration of base over acid. You need to plug it in exactly as it's written. I have the Kb. I need the Ka. 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5th gives me 5.6 times 10 to the minus 10. That's the Ka. I take the negative log of that to get the pKa value. 9.25. So pH is equal to 9.25 plus the log, the concentration of base. I have 0.1525 moles divided by 0.525 liters of solution for my base, divided by the concentration of my acid. 0.1475 moles divided by 0.525 liters. pH of this overall solution, 9.26. That 25 mils of 0.1 molar NaOH solution had very, very little effect on the pH of this solution. No surprise. It was only 25 mils compared to 500, and the concentration was much smaller than I had of ammonia and ammonium. So once it reacted, the pH did increase, and it did increase. It should increase when you add base, but it only increased a little bit. Number 12. What change will be caused by the addition of a small amount of HCl to the HF-NaF buffer? Well, if you're adding HCl, right? HCl means that you're really adding H plus or H3O plus. What's going to happen? That if you've got these both in solution, this is HF, this is really F minus. This is going to react with the F minus, the conjugate base, forming more HF plus water. We're adding H plus or H3O plus to the buffer. This reacts with the fluoride in solution. Remember, fluoride is your conjugate base. Conjugate base of a weak acid. And it will form more HF, more of your weak acid and water to reestablish its equilibrium. And then reestablish equilibrium is what I mean to say. So 1, neutralization. 2, Le Chatelier. So, which change will be caused? Will the H3O plus concentration increase significantly? No, it's going to react with it won't, because this reacts with F minus in solution. Will the F minus and H3O plus concentrations both increase? No, they react with each other. They react to neutralize. Will the HF concentration decrease and the F minus concentration increase? No. This will increase because it's going to be produced from the neutralization reaction. This will decrease because it's going to be consumed in the neutralization reaction. Will the F minus concentration decrease and the HF concentration increase? Yes. Will the fluoride ions precipitate out of solution as it's an acid salt? Nope. Soluble in solution. Sodium fluoride, sodium ions, always soluble. A 1 liter buffer solution of 0.1 molar HF and 0.1 molar NaF is a 1 liter buffer solution contains 0.12 molar HF and 0.1 molar NaF. What is the pH of the solution after I add 0.020 moles of HCl? Assume your volume change is negligible and the pKa for HF is 3.46. Again, we are adding an acid to a buffer. That acid is going to react with the base in solution. We need a BCA chart. H3O plus, my acid, reacts with F minus, my base, to produce HF and H2O. It tells me I've added 0.020 moles of H3O plus. If I look at my F minus, that's NaF, that's where my F minus comes from. I have a 0.1 molar solution in 1 liter, which is the same as 0.100 moles of F minus. And for HF, I have 0.120 molar in 1 liter solution, so 0.120 moles of HF. Subtract the smallest of the two numbers. On the reactant side, add that on the product side. I don't have any H3O plus left over. After the neutralization, I have 0.080 moles of F minus left over, and I have now, because of I've produced some more HF, I now have 0.140 moles of HF left over. Use Henderson-Hasselbalch, my pH equal to 3.46 plus the log, the concentration of base, 0.080 moles per 1 liter of solution, divided by acid, 0.140 moles, divided by 1 liter of solution. You should probably keep your sig figs there. Won't matter because your pH gives you the same answer on sig figs, but you're going to get 3.22. That is your pH of your solution. Does it make sense? I had a buffer that had originally a little more HF than NaF anyway, which means it was going to be a little bit below, the pH would be a little bit below the pKa value anyway. And then I added some more acid to it, which means the pH went even lower. So yes, this answer makes sense. Calculate the molar solubility of lead 2 chloride in pure water at 25 degrees C. The KSP of this is 1.17 times 10 to the minus 5th. So lead 2 chloride, PbCl2, is a slightly soluble salt, forming Pb2 plus and 2 moles of Cl minus. I don't have any Pb2 plus or Cl minus ions to start because it says pure water. Plus S, plus S. Again, you don't have to use S. You can use any letter you want here. We just use S to represent solubility. And I just did the mistake I always make. I get so used to doing these rice charts with a 1-to-1 ratio that I forget to write 2S. Please do not forget to write 2S. It's vital that you remember it. I only noticed because I happened to look back at my equation quick and thought, wait a minute, 2Cl minus, where's my 2? Because I know I missed that. It's an easy thing to miss. Be careful. Set up your KSP expression. KSP is equal to Bb2 plus times Cl minus squared equals S times 2S squared. 1.17 times 10 to the minus 5th is KSP. 2S squared is 4S squared times an S is 4S cubed. Solve for S. We get an S value of 0.0143 molar. The solubility here, 0.0143 molar. What about the molar solubility of calcium fluoride in a 0.1 molar sodium fluoride solution? Why does that matter? This is a common ion effect. So calcium fluoride originally I don't have any calcium present. But for fluoride, I have 0.1 molar sodium fluoride, which is the same as 0.1 molar fluoride. Plus 2S, 0.100 plus 2S. Write out your KSP expression. It's equal to S times 0.100 plus 2S squared. Now in this situation, you should check it both directions, but this is pretty concentrated. 0.1 molar is pretty concentrated compared to the solubility, especially with KSP of negative 10. So I'm going to assume that this 2S is negligible and goes to 0. And this equals 1.46 times 10 to the minus 10. Again, how did I know this? Because NaF goes to Na plus F minus. And they're each 0.1. I'm going to go ahead and keep solving this, though. 1.46 times 10 to the minus 10 is equal to X, or S. I always flip between S and X. It's bad. S times 0.100 squared. Solve for X. Blasted. S. You get 1.46 times 10 to the minus 8th molar. The molar solubility of calcium fluoride in a solution already containing fluoride ions, the common ion effect, is decreased, and we see it to be 1.46 times 10 to the minus 8th. Hydroxyapatite is the main mineral component of bone. How many grams of hydroxyapatite will dissolve in 1 liter of water? Gives us the KSP and the molar mass of hydroxyapatite as well as the reaction. So we've got 5 calcium ions, 3 phosphate ions, and 1 hydroxide ion. Let's set up your rice chart. We're going to set it up right over the answers. This would give me plus 5s. I'm going to say 5x because 5s and s's look a lot alike. Plus 3x. And hydroxide, it's a little tricky, right? 10 to the minus 7 because of water. So, and I wrote those in the wrong spot because I wasn't thinking about it. We don't have any to start. I apologize. 5x, 5x, and this would just be x. At equilibrium, 5x. I really need to pay attention. I'm sorry, you guys, I'm tired. 3x, 3x, and x plus 10 to the minus 7. I'm going to set up the KSP expression. KSP is really small. Very little amount of this actually dissolves. Probably a good thing, right? We don't really want our bones dissolving. 2.34 times 10 to minus 59 is equal to the concentration of Ca2 plus, quantity to the fifth, PO43 minus, quantity cubed, and the hydroxide concentration. Now, I am going to have to make an assumption here. Do I think that x is really small compared to 10 to the minus 7? Or do I think that 10 to the minus 7 is bigger? I'm going to make the assumption that x is bigger than 10 to the minus 7. Is it? Probably not. But I have to check both directions. What do I mean by that? The first one, let's do this. We've got 5x to the fifth times 3x to the third times x. This gives me x to the ninth. The 5 to the fifth, the 3 to the third, that gives me 84375. So 84375 x to the ninth is equal to 2.34 times 10 to the minus 59. Solve for x here. X is 8.67 times 10 to the minus 8th molar. Is x a lot bigger than 10 to the minus 7? Nope. So I have to redo the math. I have to redo it the other direction. Basically assuming that my x is really negligible in this expression instead. So because I know that the x value is smaller than the concentration of hydroxide in solution, I'm going to have to go ahead and redo these calculations. So why? Again, because I know that x is not small compared to 10 to the minus 7. That's originally there because of hydroxide. So again, I go ahead and do this. I've got 5x to the fifth times 3x cubed. That fifth should be out. Should be 5x to the fifth on the outside, times 10 to the minus 7. 5 raised to the fifth times 3 raised to the 3. Again, 84375 x to the 8th times 10 to the minus 7. 2.34 times 10 to the minus 59. Eight, 4, 3, 7, 5. X to the 8th is equal to 2.34 times 10 to the minus 53. Solve for x. Solving for x this way, I get 6.39 times 10 to the minus 8th. So not much different, but a little bit more accurate than we had when we assumed that x is really small compared to 10 to the minus 7. So this is my x value, but what is x? X is how much will actually dissolve. So now I take this number and I multiply it by molar mass of hydroxyapatite. So 6.39 times 10 to the minus 8th moles per 1 liter of hydroxyapatite. I have 1 liter of hydroxyapatite, so that gets me to moles, times 502.3 grams of hydroxyapatite per 1 mole. gives me 3.21 times 10 to the minus fifth grams of hydroxyapatite. So 3.21 times 10 minus fifth grams will dissolve in 1 liter of water. Again, good news, because I really don't want the main mineral component of bone dissolving easily in water. And our last question. Which of the following substances will affect the solubility of PbCl2 in aqueous solution? PbCl2 is Pb2 plus and Cl minus ions. 2 of them, but these ions. Basically, we're looking for anything that will create a common ion effect. This gives me Pb2 plus and NO3 2 minus, or NO3 minus, 2 NO3 minuses. So this is a common ion effect. Na plus and Cl minus, common ion effect. K plus and F minus, no effect. And both A and B, yes, that is the actual correct answer. Actually, I'll leave those highlighted. But if you're answering a multiple choice question, it would be E, both A and B.